Hello everyone and welcome back to our Summary of Reactions series. Today we will be covering a lot of the reduction reactions for ketones and aldehydes, some deoxygenation, and while we're at it we might as well cover a special type of oxidation reaction that will help us identify aldehydes. So let's start off with our reduction. Now if we want to reduce ketones and aldehydes, we can just simply use sodium borohydride. It's a really easy reagent to use, and for the ketone you just get a secondary alcohol, and for the aldehyde, you get a primary alcohol. Easy enough. Now say you have a ketone in the presence of an aldehyde, but you only want to reduce the aldehyde in that case scenario. How would you do that? Well, we need something that's a little more mild, because ketones are harder to reduce than aldehydes since aldehydes are more reactive. So if we provide a more mild reducing agent, we can reduce the aldehyde in the presence of a ketone, even if it's on the same molecule. And so instead of sodium borohydride, notice how this is very similar to it, except that instead of 4 hydrogens we only have 1, and instead of the 3 hydrogens we have 3 acetoxy groups, and so we have a triacetoxy borohydride. And if we react this, what we end up getting is that on the ketone portion of the molecule, the ketone will not react. However, on the aldehyde portion, it will react, and the aldehyde will reduce to a primary alcohol. And so this is a very useful reagent if you want to reduce an aldehyde in the presence of a ketone. Now, what's another way to reduce our ketones and aldehydes? Well, we could use lithium aluminum hydride, but that's pretty dangerous. You can actually create fires sometimes if you use it because it's so reactive, and it's a lot stronger than sodium borohydride. Another method to do it, that's instead of lithium aluminum hydride, that's a little bit cheaper and more safe to use, is using Raney nickel as a catalyst in the presence of hydrogen. Because hydrogen by itself is not very reactive, but if we have Raney nickel in the presence of that, it becomes an easy way to reduce our ketones and aldehydes. And for the ketone, we simply get a secondary alcohol, just like we had with sodium borohydride. And for our aldehyde, we have a primary alcohol. Here's our hydrogen. Now, we've finished with our reductions reaction. It's pretty easy, but we have something called deoxygenation. What is that? Well, that's the complete removal of the oxygen group on the ketone and the aldehyde. And we have 2 ways to do it. One way is with something called the Clemensin reduction. So this is the Clemensin reduction, and we use amalgamated zinc, which is basically zinc and mercury together, in the presence of dilute hydrochloric acid. And another way to do it is called the Wolff-Kishner reaction. So Wolff with 2 F's, Kishner. This is a reduction method. So Clemensin reduction and Wolff-Kishner. And they use 2 different things. For Wolff-Kishner, we have hydrazine, and then after we add hydrazine, which if you watch the previous video on some of the special reactions for ketones and aldehydes, it will provide an imine or an amine. And after we add a really strong base in the presence of heat, we can completely get rid of the alcohol group. And so, for the Clemensin reduction, this will create for the ketone just this propane, and for the aldehyde also propane. And notice how here the oxygen is completely switched with hydrogens, and the same thing goes for our aldehyde. And we get the same exact product with our Wolff-Kishner reaction. Hydrogens over here, and for the aldehyde, also hydrogens over here. Now, you're thinking like, what's the difference between these two? Why would we have these two reactions? Well, one of them has an acid, and the other has a strong base. And so, if we're looking at these two, we might think about, well, is our reactant acid sensitive? If it is acid sensitive, then we might have to pick one over the other. And so what group have we learned previously that is acid sensitive? Well, we have something called an acetyl group. If we have an acetyl group on the same molecule of the ketone, remember we can create an aldehyde. If we have an aldehyde on the same molecule, we can create it into an acetyl more readily than a ketone. That acts as a protecting group. And so if we want to reduce the ketone, say we protect the aldehyde in order not to deoxygenate it, and we want to deoxygenate the ketone by itself, we can't use our Clemensin reduction, because in this case scenario we have an acid, and the acid will react with the acetyl group and easily transform it back into the aldehyde. And so here our product will just simply look like this, where we have our product with completely no oxygens whatsoever. The ketone turned into some hydrogens, and the acetyl turned back to an aldehyde, which then furthermore got deoxygenated and just turned into hydrogens. However, with our Wolff-Kishner reduction, we can, since it doesn't contain any acids, it's actually a strong base, it won't react with the acetyl, and the acetyl will remain there and will just deoxygenate the ketone by itself. And so we get this product where now the ketone is just turned into hydrogens and there's no oxygen group whatsoever, and the acetyl group actually remains there. And so this is our acetyl group untouched by our Wolff-Kishner reduction. And so that's our deoxygenation, and we have these two different types of deoxygenating methods. One is acid sensitive and the other isn't. Now, while we're at it, we might as well cover oxygenation. Now, if we want to oxidize ketones and aldehydes, there's not much to it. Ketones are already completely oxidized, and aldehydes can only go to carboxylic acids. Now, there's this method created in order to test the presence of aldehydes in a solution, and it's called the Tollen's test. Now, we already know, well, we might not know, that silver oxide, when reacted with an aldehyde or a ketone, it will selectively oxidize aldehydes. So in this case scenario, our ketone will be untouched since it can't be oxidized, but our aldehyde will also be oxidized and turn into a carboxylic acid. And silver oxide selectively oxidizes aldehydes, meaning that if you have an alcohol, it does not oxidize the alcohol, it actually only oxidizes the aldehyde. And so somebody created a different type of group. Instead of silver oxide, they have Tollen's reagent, which is basically silver in a complex with ammonia. And this creates our Tollen's test, where it allows us to test the presence of our aldehyde, because in the end, when we test our ketone, nothing will happen. However, with the aldehyde, we get a carboxylate ion. And since we have a carboxylate ion, the silver that was originally in Tollen's reagent gets reduced, and we get this silver, reduced silver in our solution, and that can be visually seen, which allows us to see if there's an aldehyde in the solution. And so this is Tollen's test. We have our silver and ammonia complex, and allows us to test the presence of aldehydes. And that is it for our reduction, deoxygenation, and oxidation of ketones and aldehydes. And that sums up all of ketone and aldehyde reactions.